and welcome to slope as a rate of change. So let's go ahead and just consider a line, right? And then talk about slope. So slope is an instantaneous rate of change. If we consider a line just drawn in the coordinate system, right? The slope of the line was found by taking 2 points and finding the change in y value per the change in x value. Right? So this was our change in y over change in x. And slope was equal to the change in y over the change in the x value. And so we're essentially looking at how one variable changes as the other change. That's right. So this tells us how y changes in relation to x. Which is precisely what a rate of change does. So this works for a line, but if we have a curve, what are we expected to do? So next up, we have slope of a curve at a specific point. So let's go ahead and take a curve. Right? If we want to know sort of what the slope is at that specific point. So we want to know the precise slope, essentially the instantaneous rate of change. So the instantaneous rate of change should be the slope, whatever that is, precisely at that point. So let's go ahead and say that this is at C. So we're trying to find the point precisely at, or the slope at x equals C. We're going to do something similar to what we did for instantaneous velocity, right? What we can do is we can start by looking at secant lines that connect 2 points on the graph, and then slowly let those points get closer and closer together. So we will start by looking at the slope of secant lines. And then let the points get closer and closer together. So what we can do, again, I'm going to just redraw our picture and zoom in a little bit. So we have something going on like this. Here's our C. So what I can do is I can pick, let's do ones that will stand out more. I can pick, say, a point here and study the line that connects the point at C to that point. Similarly, I could pick a point somewhere on the left and study the line that connects that point to C, look at the slope. And then we can let those points get closer and closer together. So another line, maybe we would connect to a point much closer. And on the left, same thing. So we have all these lines which pass through the point at C, and we're studying sort of what happens as they get closer and closer together. So if this function is the function f, then we have sort of a series of points. Let's go ahead and use the pink line. So this point here is the point C, f of C. And this point here, what we're going to do is we're going to do kind of what we did earlier. We're going to say that this distance is h. So this point would fall at C plus h, and then f of C plus h. So we have the slope of the secant line is given by, do f of C plus h minus f of C all over C plus h minus C, otherwise known as f of C plus h minus f of C divided by h. So this is the slope of our secant line. Again, this is our difference quotient. So the slope of our secant line is this. Right? So this again is our difference quotient. Note, this is difference quotient. At x equals C. And then what we could do, if we want to find the instantaneous slope, the instantaneous rate of change, okay, so and the slope at x equals C or the instantaneous rate of change we're going to let h go to 0 of that. So we're just going to take the limit as h goes to 0 of, let me write this lower down. This is equal to the limit as h goes to 0 of f of C plus h minus f of C all over h. So again, this gives us precisely what we were working with. Also looking at the instantaneous rate of change when we were talking about velocity. So for a quick example, let's go ahead and find the instantaneous rate of change of the function f of x equals sine of x at x equals 0. So we can think of this now as we're taking essentially the limit as that h goes to 0 of these difference quotients. We're looking at a bunch of secant lines and letting the lines get closer. So the instantaneous rate of change at x equals 0, we are looking at the limit as h goes to 0 of, we know that we all have an f of something plus h minus f of something divided by h. And what is going to go into those blanks? Well, we are trying to find the instantaneous rate of change at x equals 0. So in those blanks, we will plug in 0. So we know that we are working with the limit as h goes to 0 of sine of 0 plus h, otherwise known as sine of h, minus sine of 0 all over h. This is the limit as h goes to 0 of sine of h minus, then sine of 0 is just 0. So that disappears. And we simply have sine h over h. Now, does this limit look familiar? The limit as h goes to 0 of sine h over h. This limit is, in fact, one of our special limits. We're used to seeing it with x instead of h, but it's the same thing. This is actually simply 1. So if we think about the graph of sine of x, so if we go ahead and graph sine of x, we know it crosses the origin. Then at pi over 2, we're at 1. Pi, we're back to 0. At negative pi over 2, we're at negative 1. At negative pi, we're back to 0. And if we do a rough sketch of sine, so essentially what we did was we had 0, and then 0 plus h. We went h over to the side. Okay. So from 0, let's go h to the side. And we look at a bunch of secant lines connecting the point at the origin to the point h, sine of h. And then we let those points get closer and closer together. Ultimately, they wind up at the line going through the origin with slope 1, which more or less matches precisely the sine function at that point. So this, again, is how we can go about finding the instantaneous rate of change, basing it off of essentially the slope formula, as opposed to thinking of it as something like distance over time.